Hello everybody. Let's start with the chapter called reduction formula. What is this? Over here in this chapter, we shall try to evaluate little complicated integral. Mostly this integral are computed by repeated application or repeated process of integral methods. Over here, suppose if you want to integrate simply e to the power of x or e to the power of ax, you can directly integrate it. Similarly, suppose if you want to integrate simply x to the power of n, you can integrate it directly. Over here, we shall discuss this kind of expression. Suppose if you have sine of x, we know sine x, integration of sine x, simply sine of x, that can be integrated directly. Or if we have sine square x, then making certain transformation we integrate it. But suppose we have sine to the power of 100 x, then it would be a bit difficult for us to integrate it. So in such cases, what we try to do, we designate this kind of formula. Over here we shall have to consider different kind of formula. And in this chapter, I would advise you to don't remember any formula at all. Please try to remember or try to make practice on the technique by which I am going to deduce this kind of formula. Because in exam you will be given this kind of question. These questions has been taken mostly from examination questions and from books. Suppose we have sine to the power of n x dx. Maybe n is equal to 5 or 10 or 5975. They may be very large. It may be a negative number as well. So for different cases, we shall have different kind of formula. Over here, our target is to convert this sine to the power of n into a simple or a better kind of formula, so that we can directly integrate them and get the final result. For example, over here, you see, I have a formula. I am not firstly going to show you the deduction of this formula. Suppose by certain method I am deducing this formula. Over here in is equal to the integral from 0 to pi by 2 and sine to the power of n x dx. And suppose we have already deduced this kind of formula. Then by the help of this kind of formula, what we try to do, that I am going to show over here by certain example. Suppose sine to the power of 5x dx is there, and for sine to the power of 5x dx, this is a definite integral 0 to pi by 2. If we do not have this lower and upper limit, then we shall have indefinite integral, and for indefinite integral, this is the indefinite integral. And for indefinite integral, we can prove this kind of formula. I shall discuss all this later on. And now by the help of this kind of formula, what we are doing over here, I5, that is converted into I3. Then I3 is converted into I1. And what is I1? I1 is a simple kind of formula, integral sine x dx, and that's integration is minus cos x dx. So if we now use the expression of this kind of expression of I1 into this term, then we will be able to compute the expression of I3. Now, if we use the expression of I3 in this term, then we will finally be able to compute the value of I5. And by this method, we will be able to compute the value of I5 in this fashion. So that is the technique or the kind of example that we shall have to discuss in this chapter. Over here, a complicated formula will be converted into a relatively easier formula, so that ultimately by repeated application of that formula we will be able to compute the entire expression of that kind of complicated integral. I hope this is clear to you by this kind of example. Over here, the first formula we are going to discuss is this x to the power of n e to the power of ax dx. In this kind of formula, what you need to do in your examination, you sometimes be directly given this kind of formula. If x integral of this is equal to in, you will be given this kind of question. If in is equal to this, then show that in is equal to this right hand side. You will be given this kind of direct questions. Okay, then how to prove? You see, we already had a formula for integration by parts. LIATE. LIATE. Liat. L for logarithmic function, I for inverse function, then A for algebraic function, then T for trigonometric function, and E for exponential function. So over here, x to the power of n is an algebraic function, so third option is there, and e to the power of ax is an exponential function. So this first function x to the power of n should be taken as the first function u, and then e to the power of x should be taken as the second function. Got it? Over here we are taking this x to the power of n as the first function. Then what we have, this is very easy. This is the first function, and then this is the integral of second function, e to the power of ax. Whenever it is integrated, we will have e to the power of ax divided by a. Then minus, this is the derivative of x to the power of n, derivative of first function, n into x to the power of n minus 1. Then integral of second function, e to the power of ax divided by a. And afterwards we are keeping this first term same as this expression, and then this n divided by a has been kept outside the integral sign. Then finally we have x to the power of n minus 1 into e to the power of ax dx. So you can observe that if we have in, an integral involving this index n, got it? An integral involving this index n, and over here in place of n, what we have? Over here we have n minus 1 in place of n. So this total integral can be written as in minus 1. Got it? So we are writing this integral, this second integral, as in minus 1, and we finally have this kind of result, that in is equal to x to the power of n by e to the power of ax divided by a minus n by a into in minus 1. So in this way we can obtain a relatively simple integral. Why simple? Because over here we have the number of index becomes smaller. Suppose n is equal to 5, then from 5 we will get i4, the index would be 4. Now apply it for i4. For i4 we will get i3, for i3 we will get i2, for i2 we will get i1, and so on. So ultimately this expression will be simplified, and finally we will be able to compute the expression of this entire integral. So this kind of formula are actually called reduction formula. So you don't have to remember this kind of formula. Just try to remember the technique. I don't remember any of this formula represented over here. You see an example has also been there. Over here x is taken, n is taken as equal to 4. So we have i4. Just put n is equal to 4 in this formula. Firstly you need to deduce this formula, and then in this formula you will have to put n is equal to 4. Then we have this kind of result that is related with i3. Okay, then apply, put n is equal to 3 over here. Now compute the expression of i3 in terms of i2. So what we now need? We now need the expression of I2. Therefore, we put n is equal to 2 and we get the expression of I2 in terms of I1. Got it? And afterwards, we just put n is equal to 1. So we get the expression of I1 in terms of I0. Now, what is I0? I0 would be just put n is equal to 0 over here. So x to the power of 0 would be there. X to the power of 0 means 1. X to the power of 0 means 1. So I0, capital I0 will have x to the power of 0. That is actually 1 into e to the power of ax. Okay. So we actually have x to the power of 0 into e to the power of x. That is simply is equal to the integral of e to the power of ax, and e to the power of ax, when it is integrated with respect to x, we will have e to the power of ax divided by a. So now we know the expression of I0, and if we put the expression of I0 in this right hand side, you will be able to find I1. Then put the expression of I1 over here, you will be able to find I2. Then put the expression of I2 over here, you will be able to find I3. And finally put the expression of I3 over here, you will be able to find I4. So in this way, they have directly written the final result, but you will have to show the entire computation. And along with that, after integration, we know that an arbitrary constant arises in case of indefinite integral. Therefore, you will have to finally put an arbitrary constant c. Don't forget to put this arbitrary constant, because this is the most crucial part that you generally forget. Generally, you become so much happy after computing this much that you forget to assign an arbitrary constant. Okay, so be very careful on it. So this is the first kind of an easy formula that we discussed. Now I am going to discuss this integral of sine to the power of nx dx, and that would be the last formula for today, because already it is about 1 hour. Hmm. So I am discussing the formula from this file over here. Sine to the power of nx dx. So n is the index. Over here, n is taken as a positive integer. Hmm. So now what we need to do? We need to convert this integral into relatively less number of into an integral having less number of index, smaller index. Okay. So what we are doing over here? We are separating one sine x. We are separating one sine x, and sine to the power of n minus 1 x is there. Now you see this formula, this sine to the power of x, this function is easy to integrate. Over here, it would be very difficult to make the decision that which function should we take as the first function and which function should we take as the second function to integrate this in as a by partial fraction. Hmm. So by not by partial fraction, actually by parts. Hmm. So we need two functions. One is function u, the first function. Another is the function v. Over here, you see this second function is mostly whenever the v function is generally integrated in the integration by parts. So this function is easy to integrate. So that's why I am taking this function as the second function. And this function is easy to differentiate. Got it? Generally, the first function is differentiated, and the second function is integrated in the integration by parts formula. Okay. So we are taking this as the second function, and this is the first function. So by integration by parts, first function into integral of second function minus derivative of first function. So sine to the power of n minus 1 x, when it is differentiated, we will have n minus 1, then sine to the power of n minus 2 x, and then by chain rule, sine of x has to be differentiated and we will get simply cos of x. So this much would be the differentiation of first function. Got it? And then along with this we need to multiply the integration of second function. So sine x, whenever it is integrated, we will have minus cos of x dx. Got it? And this minus sign along with this minus sign outside the integral would construct this positive plus sign. So this first term is kept fixed. Then along with this plus, this n minus 1 is taken outside the integral sign. We have sine to the power of n minus 1 and then cos x multiplied by cos x. They would construct cos square x dx. And now this is the tricky part of this kind of questions. Cos square x is now written in terms of 1 minus sine x. Why? Because our target is to convert everything in terms of sine to the power of n or maybe n minus 1 or n minus 2, not any expression involving cos, because already we have sine to the power of n kind of integral. Okay, so over here we observe that if we now apply the formula that cos square x is equal to 1 minus sine square x, then after decomposition, this formula would be written as sine to the power of n minus 1 dx, integral of sine to the power of n minus 1 x dx, minus integral of sine to the power of n x dx. So this formula is equal to I n minus 1 as per this notation. Over here in place of n we have n minus 1. So this integral can be written as I n minus 1 and this integral is again the original integral I n. So I am writing I n minus 1 minus I n over here. Now this expression involving in is taken left hand on the left because we started with in. So on the left hand side we have in and on the right hand side we have in minus 1 along with in. So keep all this in on the left. Got it? So this whenever this n minus 1 multiplied by in is shifted on the left, then this negative sign will be converted into positive sign over into this plus. So if we take this in common, we'll have this kind of expression inside the bracket and the remaining portion is kept on the right hand side. Okay, so this 1 and this minus 1 will get cancelled. Only we will have n into in on the left. So now what would be the expression of in? Just divide the entire expression by n. You will get the expression of in. Now you can ask me, where is the constant of integration? That is a vital question. Generally in this kind of reduction formula, you wouldn't find any constant of integration. The constant of integration is mostly introduced at last, as it is done in this kind of formula in this last example. Because the constant of integration generally written at last, but it does not mean that there is no constant of integration in the intermediate steps. All the constant of integration are then added and finally the entire contribution is written over here as plus c. All the constant of integration are added and the entire contribution has been written as a single constant of integration plus c. Got it? So this c contains all the constant of integration that arises in all the previous portions. But over here in this computation we are not writing any constant of integration. Why? Because the constant of integration, we can say that the constant of integration can be adjusted in this integral, in this in minus 2. So this in minus 2 already contains a constant of integration. That's why we don't need to individually write any constant of integration like plus c, because ultimately it would not be of any use at all. That's why this is the convention that we always write everything without constant of integration in this kind of reduction formula. Only the constant of integration is written after completion of the entire computation. Got it? So this is the reduction formula for sine to the power of n x dx. And in some examples, the lower and upper limits are also specified. Lower limit may be 0, upper limit may be pi by 2. So if we are given this kind of lower and upper limit, then in each and every step, you will have to apply lower and upper limit. Maybe this kind of lower and upper limit, maybe 0, and maybe x is equal to pi by 2, pi divided by sorry, pi by 2. This kind of maybe pi by 2. So sometimes what happens is that maybe due to use of this application of this lower and upper limit, you see over here at the lower limit at x is equal to 0, this sine of x would become is equal to 0, and at upper limit x is equal to pi by 2, cos of x would become is equal to 0. Therefore, it would be sometimes advantageous to use uh, this kind of lower and upper limit, then ultimately you will find that this first term would be vanished by putting the this lower limit and upper limit. So sometimes the computation becomes a bit easier in case of definite integral. Got it? And if you don't apply the lower and upper limit, suppose you already have this kind of formula, then what to do? Then just apply the lower and upper limit in this first term. Okay, so if you apply the lower and upper limit in this first term, you see this term with at the limit lower limit 0 and upper limit pi by 2, at lower limit x is equal to 0, this term would get cancelled, and at the upper limit pi by 2, this factor would get cancelled. So ultimately no contribution would come from this first term, and that's why we will have for definite integral with 0 and pi by 2 as the lower and upper limit, we will have this kind of reduction formula. And one example has been studied over here. As I told you earlier, that I5 is written in terms of I3, and then I3 is written in terms of I1, and I1 is now directly integrated, and finally we'll get a constant of integration C1. Got it? So if we now use this expression of I1 in over here, we will get the expression of I3, then expression of I5, and so on. Finally, whatever we have, we are writing all the contributions in terms of C. So C would be is equal to 8 by 15 into C1. So this is the computation portion that I have shown over here. Thank you for having with me and for your patience with this class.